Welcome back. So we have been looking at recurrence relations. So recurrence relations is basically a sequence of numbers where the initial set of numbers are given and the nth term is defined as a function of the earlier terms. And we have seen that recurrence relation is used extensively in combinatorics, analysis of algorithms and various other subjects. So there's two things. First of all, recurrence relations can be used to model various counting problems. And once we model the problem using the recurrence relation, we need to solve the recurrence relation. Now, question is how to solve the recurrence relation. So here are some of the recurrence relations that we have looked into in the last few videos. And the question is how to solve the recurrence relations. So the first one that we learned was that we can guess the solution and then prove by induction. Now this is fine. If you can correctly guess it, then you can use induction to prove it, and that's pretty standard induction proof. But how do you guess the solution? Now there is no one way of guessing the solution. One simple one is what we call as unfolding the definitions. So by unfolding the definitions, we can possibly guess the solution. And we saw how this can be done for this set of recurrence relations. But then there are equivalence relations which are very hard to guess. One of the reasons can be that the recurrence relation itself is very complicated. For example, the Fibonacci number, this is a pretty complicated thing, so you don't expect to guess this one easily. And secondly, there are examples where there are things like floor and ceiling in the expression, and which are pretty complicated to work with also. So there is no nice guess that can be there. So we looked at this particular example of mn equals to m ceiling of n by 2 plus m floor of n by 2 plus n. And instead of guessing, what we could do is we can upper bound and lower bound the mn by some value. And the question was that, can we do better than that? So we could not guess the actual value of mn, but we could upper bound mn by some value, lower bound mn by some value, and these two values were not too far from each other. Sometimes this gap that is there between the upper bound and lower bound, which is the 4 times gap, is small enough that we don't care about improving it. So how can we compare whether we have done a good job or not? And for that we need to work with something of the what we call as asymptotic notations. So here are some of the questions that are asked. For example, in the earlier case, how can we compare mn with n log n? Or which is bigger, n power 4 or 2 power n? Or is n factorial similar to n power n? And what about these two numbers, n squared and n squared minus n log n plus 100n? Now, we know that given two functions, we can say these two functions are equal if they are same at all points. We can also say that one is less than the other if it is less than the other at all points, and so on. But sometimes if we are not worried about the initial set of numbers, meaning we are only worried about what happens when n is large, when the domain is large, and we are only concerned about things up to a constant multiplication, we use what we known as the asymptotic notations. In the last video, we explained the asymptotic notations carefully. For example, we say f is big O of g if fx is less than some constant times gx. Similarly, we say f is theta of g if f is big O of g and f is omega of g, big omega of g, which means, so this big omega of g means that f is bigger than constant time gx. We have something called f is asymptotically similar to g if fx by g tends to 1, and we say f is small o of g if limit as x tends to infinity fx by gx is equals to 0. So in fact, with this set of asymptotic notations in our hand, we can now try to solve the recurrence relations. Now, the first thing to note is that so there are some examples here that we did last time, namely, if when we are comparing two polynomials, all we have to look at is the maximum degree. Similarly, a polynomial is always small o of the exponential. A polylog is always small o of any polynomial. 2 power n is small o of 3 power n. And we also looked at two asymptotic approximations to two useful things, particularly this first one, which is n factorial is asymptotically equal to square root 2 pi n times n by e power n. Now, once we have these asymptotic notations in our hand, and someone has given us this kind of a recurrence relation, we should try to do the following. When we are guessing it, the first thing, if we can, is try to give a exact formula for mn. Now this is as good as it gets. If you can get an exact formula, that is wonderful. Now if we cannot, second one that we can ask is, can we say that mn is asymptotically similar to some number? That's the second option. Third option, okay, I cannot even prove that mn is asymptotically equal to some option. Third option is mn is theta of something. And the fourth one is, okay, I cannot prove mn is theta of something, but can we give you an upper bound, and can I give you a lower bound? And now this is basically the way in which you should go about it. If somebody gives you a recurrence relation, you should first try to see whether you can come up with an exact formula. If you can get the exact formula and prove it by induction, as we have done in earlier some of the examples, then great. If not, can you prove as asymptotically equal, asymptotically similar notation? Or can we prove, if I cannot prove asymptotically similar, can I prove that it is theta of something? And if I cannot prove if it is theta of something, can I at least give you an upper bound or a lower bound to this? Okay, so this is the way in which a recurrence relation is solved. Now, question is that how do you go about solving this one? So let me give you a couple of examples. We'll go through a couple of examples and we'll see how one can use asymptotic notations or get solve the recurrence relations using asymptotic notations. Now, once you have been given this one, the first thing to do is, can you guess mn, if not for all n, but for some n? Now, as we did it in this case, that when n is a power of 2, we can guess mn equals to n times 1 plus log n. Now this is good, but once I have this mn is 1 plus log n, note that this 1 plus doesn't make much difference because as I told you, these are polynomials, so the big term only matters. So this is basically nothing but n log n. You can check, of course, that this value mn equals to 1 plus log n is not the exact solution to mn for all n. But by now we have got a handle that mn is somewhat like n log n. The next step to do is by induction prove mn equals to theta of this number, theta of n log n. Now, what do we mean by theta of n log n? Theta of n log n has actually two parts to it. One is an upper bound, that you have to prove that mn is less than or equal to cn log n for some c, and then you prove mn is bigger than some d times n log n for some, so this is the d, for some d. And once you are done with that, then you get that mn equals to theta n log n. So I don't want to do this, solve these problems right now. I would like you guys to, as you are watching this video, to solve them by yourselves. Of course, for this particular problem, mn, we have already done it. We have proved that mn is equal to 2n log n and mn is greater than half n log n. Now, the important thing to know is that how can you choose this c and this d? And the way to do it is that you assume that mn is less than or equal to cn log n, and you go over the whole induction reasoning, the induction hypothesis and inductive step, and see if you can come up with some c for which this inductive step goes through. And if it can be done, then you have this c log n upper bound. Okay. So here is one more problem. b1 equals to 1 and bn equals to b floor of n over 2 plus 1. Again, we need to first guess bn for some n. And as you can see that again, since I am getting n over 2 floor, so we have to somehow choose the n so that n over 2 is always a integer. And I don't have to, I can throw away the floor and so on. And that can happen if n is a power of 2 again. So even here you can convince yourself that, and you prove it. I would like you guys to prove it while you are watching this video, that if you put n equals to 2 power k, then bn equals to k, which is log n actually. This will be k. And now once you are done, again, see that this bn equals to log n is not an exact answer to bn. So instead of solving it exactly, you prove by induction bn equals to theta of log n, which basically means that you prove that there is an upper bound on bn, which is c times log n, and for some c, and a lower bound of bn, which is something like d times log n plus some t for some t. Now, if actually you get these two things, you get this theta. Okay. If actually you can get the c and d to be arbitrarily close to each other, for example, c equals to d plus 1 by n kind of stuff. So as n goes to infinity, c equals to d. If limit as n goes to infinity, c equals to limit as n goes to infinity, d, then what we have is that Bn will become sim of log n, which is, as I told you earlier, better than getting theta of log n. An important point here is that you should always reduce, when you have to prove this induction thing, you should always reduce into these two parts and prove it individually. When you are proving this inductions, don't use any asymptotic notations. Asymptotic notations are just some nice language that helps us to say how the function is going to behave in the long run, and doesn't say anything about the exact value of Bn and or any such things. Okay. Okay. So here is one more example here. So if Tn equals to order n plus Tn over 5 plus T7n over 10. Now what do I mean by this statement? When I have something like an order n right in the expression, what it means is that there exists some a for which Tn equals to a times n plus Tn over 5 plus T7n over 10. Now this kind of an expression is used a lot in the analysis of algorithms, where when we count, we are not exactly sure of the constants. So instead of putting a constant here, say 5n or 3n or something, we just leave it with the order n. And this is how you are supposed to read it. Okay, so Tn is equals to an plus Tn over 5 plus T7n over 10. And now if you have this one, you have to guess again, first thing, Tn for some n. Now here again, as you can see, we have to ensure that I can guess it by, of course, ensuring that n is divisible by 5 and n is divisible by 10. That means n is of the form 10 power k, and in that case you would be able to guess that Tn equals to theta n. In fact, if you solve it, what you will get is that, so Tn equals to an plus Tn over 5 plus T7n over 10, which is, if I now expand Tn, this is a times n over 5 plus T n by 25 plus T 7n by 50 plus a 7n by 10 plus T 7n by 50 plus T 7n by 100. Now the point to note is that by adding this one, I will get an plus 9 by 10 n plus something which are this term. Now if you expand it once more, what you will see is that I am getting some term like 9n by 10 whole square. In fact, I should get exactly that, plus something, this after you expand it the second time. And summation of this an time plus 9n by 10 plus 9n by 10 whole square and so on is, okay, it is some number, it's a n times something like 10n, 10a or something. So in other words, you cannot guess this thing exactly again, even for the special case of n equals to 10 power 5 and so on. But what you are able to guess is that Tn is something of like theta n. And now you prove this one first of all again by induction, and in which case you go back to your same technique. You prove an upper bound of saying that Tn is less than C times n for some n, and then you prove that Tn is greater than B times n for some n. And by doing so, you will be able to prove that Tn equals to theta n. Now, this is Tn. Now, as I told you in the beginning of this course, solving problems is basically the only way of understanding it. And here is a template of how to attack this problem. And you can go over it. You should follow this template and try to solve these two examples that we have given here. In the next class, we will see how to come up with a general technique of solving this problem. We will see a theorem that will help us to solve it.